All demonstrations in this video were computed and rendered in real time on a 1.8 GHz Pentium 4 PC with a GeForce 4 graphics card. The grossly deformed pitbull model shows the inaccuracy of the linear finite element method in connection with large rotational deformations. With our warped stiffness approach, the artifact disappears. Our elasticity model is as fast and stable as the linear finite element method, but produces much more accurate results for arbitrary deformations, as the snake shows. Here we use 440 tetrahedra and 22,000 surface triangles. In contrast to the vertex-based warped stiffness approach, our element-based technique produces correct animations of free-floating objects without ghost forces. The dragon model we use is composed of 830 tetrahedra and 10,000 surface triangles. With the parameters of our plasticity model, we are able to simulate a variety of elastoplastic materials. This aluminum cow exhibits nearly perfect plastic behavior by storing deformation energy almost completely. This free-floating cow is made out of elastoplastic material. Part of the deformation is restored, while most is stored in a permanent change of shape. The cow model contains 970 tetrahedra and 5,800 surface triangles. Very low plastic yield and high plastic creep yield a material similar to warm wax. The cow deforms under gravity alone while its back is held fixed. When the maximum plasticity of the material is reduced to zero, the cow recovers to its original shape. With another set of material parameters, we are able to simulate a Play-Doh dragon. The model allows almost arbitrary twisting and bending deformation without becoming unstable or unrealistic. This simple wall model demonstrates our tearing and fracture procedure. When the internal stresses, shown as red bars, exceed a material threshold, the mesh is fractured along tetrahedral boundaries. In this example, a detailed surface mesh is fractured along with the coarser tetrahedral mesh. New surfaces, shown with the darker texture, are generated dynamically while the model is torn apart. Here we only show the vertices of the underlying tetrahedra to demonstrate the process of generating new surfaces at the tetrahedral boundaries. While the dragon is torn apart, it collides with itself to demonstrate self-collision and collision response. Every tetrahedron can have its own set of material parameters. Here, a virtual heat source changes these parameters for each tetrahedron individually. With increased temperature, Young's modulus and the fracture threshold are reduced while plastic yield and plastic creep are increased. Here we start with the stiff material. We first reduce Young's modulus by a factor of 100. Then we increase the density by a factor of 6. The Poisson ratio controls the conservation of volume visible in the thickness of the dragon's body when stretched. The simulation yields meaningful results, even for extreme material parameters.